In this final video, I'll give an overview of stacking models, otherwise known as heterogeneous ensembles. The approach here is akin to parallel homogeneous techniques such as bagging. Essentially, separate machine learning models are trained independently in parallel and then combined at the end through a second stage learning model. Thus, in practice, you have all the tools that you need to implement them, so I will instead focus primarily on examples of how they are used. So the key is to train as diverse models as possible. For example, at the first stage, train support vector machines and trees or forests or boosting models, all on the same data, or bootstrapped samples from the data, or subsets of the feature space. Then, in the second stage, you take the outputs from those models and you combine them. For example, let's say you trained 5 models in the first stage, and those will return 5 different predictions for each training example. Those 5 predictions then become features in a second learning stage. This can be as simple as a majority voting, but equally it can be an entirely separate machine learning model, such as a support vector machine or a forest. So that's it essentially, although that of course still generates huge amounts of flexibility. And for those reasons, stacking ensembles feature strongly in machine learning competitions such as those seen on Kaggle. Examples of how they're used in biomedical imaging include the ICA-X noisifier from the Oxford group FIMRIB. So here the idea is to train a classifier to check all the ICA components that come out of a resting state functional magnetic resonance imaging analysis in order to detect which ones represent neurological signals and which reflect physiological or image acquisition noise. This here, for example, is a component which reflects the influence of cardiac pulsation on the blood flow to the brain, which, because functional magnetic resonance imaging or fMRI indirectly infers brain activity from blood oxygenation, is a problem. FIX therefore uses a large number of handcrafted features designed to capture different properties of the ICA spatial map and the component time series. These are then trained on support vector machines, k-nearest neighbour classifiers and decision trees, and then passed to a second stage random forest stacking classifier. On the other hand, the ensemble EMMA, nothing to do with me incidentally, combines an ensemble of separately trained deep learning segmentation models. Each use very different architectures. The results are then combined through simple majority voting to improve the performance of deep learning based brain tumour segmentation. And this is an example of a method which tries to simultaneously condense and combine the vast amounts of different types of MRI data available for modelling brain structure, for example, functional imaging or features of brain shape and composition, in order to build more sensitive models for the prediction of fluid intelligence or other metrics of cognition. For this, it uses lasso regression at both stages of the stacking model, firstly taking each modality separately and performing a PCA to reduce dimensionality, and then training a lasso. Then, at the second stage, these predictions are combined to give a final score, also using lasso. So in summary, stacking is simply the process of training separate machine learning models on the same training data and then combining their predictions. Best performance is achieved by training diverse models of very different types. Diversity may be increased through bootstrapping data examples or training on different subsets of features. The idea is that these predictions are combined through a second stage meta-learning model, which can be as simple as performing majority voting, but also often uses a second stage classifier or regression model, where the features of this second stage are the predictions from the first stage. Naturally, there is a huge amount of flexibility in how this can be done, and so in this way, stacking approaches are repeatedly proving themselves as powerful techniques for improving the precision and generalization of models. So that's it for my portion of the course. I hope you found it useful. Don't hesitate to contact me either through the discussion forum or privately via email or Teams if you have any questions or need any help on the content from these past few weeks.